Hello everyone. I know I've been meaning to make these videos for a while now. Life's just been getting super busy, so sorry for that. This is just going to be a quick overview of Star-CCM. I'll make more detailed videos on different parts of the design tree in the future, but yeah. So when you start Star-CCM, this will be the window that you'll see. So you got to either make a new file or open a file. So creating a new file brings up this window. And then opening a file, which is what I'm going to do because I have the old Sims, will open up this window. So, process options, serial, is just using one core, so that'll be slow, so always go for parallel. Pretty much everyone should have multi-core computer at this point in time in history, but, anyways, yeah, so because I'm recording, I'm not going to use all 8 cores I have available, so I'll just use 4. You'll want to make sure power session, power on demand is checked off. Make sure the server is that. Make sure your power on demand key that you'll be given is input in. And important thing about this is that this will not work on ASU's Wi-Fi. Star-CCM and ASU's Wi-Fi don't like each other, the servers, so you either have to use a mobile hotspot, or you have to go and basically do it at home or somewhere else. So anyways, I'm going to browse and find the file. We're going to open it. I'm going to give Star-CCM a couple seconds to open it. They're pretty big files. They're a couple of gigs in size. So this is the window you'll see when you open Star-CCM. Up here is a toolbar of various tools. Up here is that menu, whatever you call it. It basically has these toolbar functions in it as well. This over here, I'm going to call it the design tree. I don't actually know the proper name. I'm just taking it off of like CAD and all that stuff. And down here is a properties window. So whenever you select something, the properties window will change whatever is in here to fit. So I know it can look a little overwhelming with all these options, but generally you basically just go from the top and work to the bottom. So first you need to import geometry. So you use this what looks like an upside down Triforce symbol here. And so scenes down here, I know they're at the end, but these are important because this is what helps you visualize what you're looking at. So when you import geometry, it'll make a geometry scene. When you make a mesh, it'll make a mesh scene. So I'm going to open these up real fast. And geometry scene, as the name implies, is the geometry that you import. So this is a cavity. When you import it in fresh in Star-CCM, you won't have these colors on them. This is because they've already been identified as regions, which you can see down here. We'll get to in a bit. But yeah, so this is a cavity. You have to import these as a Parasolid file. These came from SolidWorks. So alright, let's go and start off with geometry. So let's say we imported a geometry in already. What's going to happen is that you're going to have this under parts. Now, Star-CCM does this thing sometimes where it for some reason it thinks that even though you only have one part imported, it thinks there are multiple parts. In this case, it thinks that there are 2 bodies, even though there's only one body. Now, let's give it a sec to load, because when you select, so in general, if you select these things, be careful. Sometimes it may cause the program to kind of freeze up for a sec because it's trying to select everything in it. But anyways, it thinks that there are 2 bodies in here when really there's only one. You'll see that when Star-CCM decides it will load everything, this is only like one face for some reason. This is something that we weren't really able to figure out. So if you can figure that out and do it, not have this problem, that'd be cool. This really isn't too much of an issue though, so long as there's not self-intersecting geometry. You'll know what that means. You'll know that's an error when you get it. It will basically show up it won't let you mesh at all. But anyways, you can see, this is the second body Star-CCM thinks that exists. We don't know how to get rid of it, but as I was saying, it's not a problem so long as you mesh the entire assembly, and like when you select a region, you select everything, so that way you don't leave it out. But yeah, so body 2 you can see is everything else. Now, in geometry, you'll see that there are surfaces and curves for every body. You don't really need to worry about the curves, but surfaces are important because this is what you'll do to split up all your surfaces into individual ones, and this will be important for tracking downforce drag, as well as labeling all of your boundary conditions as well. So you can see how like even the domains are named. You need to do this. So super important step. what you'll do is you'll split by patch, so like you just right click. So when you import it in, everything will be one surface, and what you'll do is like you'll go split by patch, and then you'll see that the surfaces are all like this. You'll select various surfaces, and then you'll sit like name it a new name, and then just hit create. But yeah, so once you do all that, then you gotta move on to meshing. So meshing can be found under operations, and then you'll go to new mesh, automated mesh. So meshing in Star-CCM, I know there are probably better ways of doing it than I did. There are definitely better ways of doing it than I did. I just didn't have the time to look up those different ways. So I have my automated mesh, and again, it'll generally make a mesh scene when you do it. So the way Star-CCM works, it makes a surface mesh first, but then it makes a volume mesh. So surface mesh is a mesh of all the parts on the surfaces. So you can see here, this is the surface mesh of the car. Now, the volume mesh, I will load here, is going to be representation. It's like a projection of the volume cells that are touching the surfaces. Now, I didn't figure out how to show the volumes themselves, like, you know, like how you can see in ANSYS. Oops. But if you can figure that out, that'd be good. Also, if you can figure out how to refine by volume, so like you'd want half the car length in front, full car length in back, to be more further refined, because I know I'm wasting a lot of space, resources on these cells, because they're not fully, they could be coarser, and then closer up they could be finer. So anyways, a little aside there. So also, another important thing is, for wheels, for example, if they're touching the ground, you want to make sure that they actually go through the ground slightly. Otherwise, you're going to get some funky surface conditions that are going to break your sim. So that's actually a pretty important detail. So make sure that you're always basically going through the ground slightly. Anyways, so let's go back to meshing. So these are the meshes I choose. Surface mesher makes a surface mesh, polyhedral mesher makes a volume mesh, and prism layer mesher. So prism layer mesher is important because you can see here that it creates prism layers on the surfaces, and this helps capture the boundary layer growth on the surface. Now, there are ways of calculating how tall this should be. I didn't really do that because I didn't know about it at the time. So this is kind of just done by trial and error here. You can see it could be a little better, but it's done its purpose. So once you make the mesh, you'll see that you have all these controls, right? So again, I'll make a more detailed video on it, but this is how you control the details of your mesh, like how big the cells are, how well it wraps around curvatures, etc. This is the global setting, default controls. Custom controls, you go down here, you can specify surfaces. So like, you'll go down, make new surface control, and what you'll do is down here under part surfaces, you'll choose which surface you're specifically talking about, and you'll go and refine. You can go ahead and do all these controls, but specifically for that surface. And that's why you can see like the body is coarser than, say, the wings, is because I have different custom controls for the wings versus the body, which has different values and all that. So the mesh you see here, I didn't do a convergence study or to really check the quality of. You should be doing that, but given that our flow visualization over the summer matched the CFD pretty well, I feel that this is pretty good. So yeah. Next up, you'll have continua. So continua, your parts meshes should automatically be made once you generate a mesh. Physics, you have to go and say new physics continuum, and this is important because this is the physics of the model. So when you generate it, what's going to happen is you're going to come up, you're going to have, actually I'll just start from scratch just to demonstrate. So under models, you have to choose all these different options. So obviously, I'll make a more detailed video about what this is in the future, but just know that like these are the options that I've chosen. So we use K omega SST. A little overview: K omega SST is a 2-equation turbulence model. K omega itself, K epsilon, K omega are the same, just reformatted with the different. I forgot the name of it, but yeah. K omega is better away from surfaces, K epsilon is better close to surfaces. K omega SST uses the K omega model, but a blending function with K epsilon, so that way closer to surfaces it resolves things better. That's the reason why we chose K omega. We chose constant density as well because we're assuming incompressible flow. So anything below Mach 0.3 you can assume is incompressible. So under gas, air, material properties, you need to change this density because it has a different default value than the one we use in class. So just change that to 1.225 kilograms per cubic meters. This is all chosen when you're choosing those models, so you don't really need to worry about this stuff. I also don't really change any of this. So that's all I need for here. Let's go ahead and delete this because we don't need it. So after that, you'll go and make your regions. Now, this is why splitting all the surfaces was important, because the regions are, as the name implies, well, a region, it's a boundary. So default, it's just nothing you selected. Ooh, actually, that should be a symmetry right there, but whatever, it's fine. So what you'll do is you'll select a region, say like this is the front wheel. Now, well, actually, let me go through it this way. So you need to find an inlet, right? So you need to tell Star-CCM on which surface is air flowing into, and in this case we have velocity inlet here. So you have to specify flow direction, so in this case boundary normal, so it'll go inwards, and then like you have to specify the magnitude of it. So in this case 35-mile-an-hour air is flowing normal to the velocity inlet, so it's going in. And actually that reminds me, I forgot, my bad. Under physics there's initial conditions. This is important. So this stuff you don't need to select, change, but velocity, you want to initialize velocity. What this does is it makes in the domain, this will make sorry, this thing is kind of tricky sometimes. This will make all of the air inside the domain be 35 miles an hour. That's important because if you don't initialize it, part of the sim will involve waiting for the air to go from the inlet to the car. So you'd be wasting time computing that, whereas you can just make everything 35 miles an hour, and by having the inlet give 35 mile an hour air inwards, it's just sustaining that initialized air. So don't forget initial conditions, that's important. Almost forgot about that, my bad. Anyways, yeah, and then so you'll be defining, say, a pressure outlet. Now the pressure outlet is just telling Star-CCM this is where pressure can get relieved. Now you want to use a pressure outlet and not just outlet for reasons that I can't really explain right now. I'm not entirely sure, but make sure it's pressure outlet. And you don't really need to change any of the settings here. And again, so although surface splitting is important because now you specify, say, the wheels, because the wheels need to be specified as rotating, because rotating wheels have much different aerodynamic properties than non-rotating wheels. So like you'll have to go and say it's local rotation rate, and then you specify the axis, which you have to pull from CAD, and then the angular velocity of the wheel. Furthermore, you need to say that the ground plane is moving as well, because the car is moving. So relative to the car, the ground's moving. So you go and say vector, and then you'll say that it's moving same as the airspeed. And then you need to make sure that you apply symmetries. So symmetry basically says that it mirrors everything. So anything that is happening on one side will happen on the other, and that's what will allow it to... That's why we can run half a car, because we're saying this is symmetry. There's a car on the other half's on the other side. The other half's on the other side, and it's doing the same thing. So also you want to define the top and the top and the side here as a symmetry as well. That's just how I've been recommended to set up these sims. I can't explain entirely why we do that, but yeah. So that's all for boundaries. You don't need to worry about any of this stuff because this is for the global domain. So derived parts, I'll get into that a little while later. You can make them now, or you can make them for scenes, but I'll explain them in context of the scenes. It'll make more sense there. Solvers, these are how the program solves the equations, the physics that you use. So here you can specify time steps. So we're using transients. You're using a transient simulation because the turbulence region we're in right now, it won't necessarily come to a steady solution. So you can specify a time step, and then temporal, basically what order that it solves it on. So second order is a second order equation, more accurate, use that. Time step, in this case, we again, there's a way to properly calculate this, but I kind of just did this through trial and error, and we settled on 0.1, a tenth of a second. And so that means that the simulation will run for every tenth of a second increment. So like, you know, 0.1, 0.2, 0.3 seconds after everything's initialized. So you don't need to worry about any of this stuff. Stopping criteria. So first, make sure maximum steps is unchecked. This is how many steps it'll take. I don't like doing that because you can specify the time step here, and in maximum physical time you can specify how long will the transit simulation run to. So in this case it'll run to 3 seconds, and it'll stop there. Maximum inner iterations, this specifies how many iterations each time step runs through. So in this case we have 75 iterations per time step, so it'll iterate 75 times in the 0.1 seconds, then it'll move on to 0.2 seconds, iterate 75 times, and it'll keep moving on until 3 seconds is reached. Stop file, go ahead and leave that. Solution history. Now, make a solution history, let's say new, then you have to, it's a SimH file, and you have to name it and save it in a specific place. Now, this will save all of the results that you select for something. So, like, you can save various functions here into the solution history, and it'll record all of that. Now, I think this has to do with, like, your StarView files if you make those, but I never really figured out how to use them properly. But, you know, if you want to keep them, go ahead. Solution views, don't worry about that. Reports, this is important. So this is where the bread and butter, this is where you actually find the numbers. So downforce and drag are force reports. Lift and drag coefficients are force coefficient reports. So you go to new report, and then you'll see either force or force coefficient right here. So on a force report, you specify the units, the coordinate system, laboratory means global, the direction. So you see how you have the directions here. Make sure that, you know, like your downforce is in the Y direction and your drag is in the Z direction that's specified here. Pressure and shear you want, and then reference pressure is just gauge pressure is 0. And this is why it's important to split everything up. So this is where you can see how everything is selected. This way, A, we don't select the boundaries so we don't screw up our numbers, and B, when you run the report, so you double click it, it'll make a report down here. It will split everything up according to like those elements or those surfaces, so you can see exactly how much downforce, say, the first element, the front wing makes, or you know, so it helps for analysis. And what I was going to say is, or like, you know, the drag coefficient. So let me go over force coefficient reports first. So again, specify the coordinate system, the direction, force option, pressure and shear, you want all of it. And also make sure that, again, if you know the lift and drag coefficient equations, you need the density, the velocity, and reference area. So density, we said already, 1.225. Reference velocity, it's the one that we use, 35 miles an hour. And then reference area is the frontal area of the car. That's why there's a frontal area report here. So, and so you can run that, and again, it will show like the exact drag coefficient of every part. And then it'll total it down here like this. So, yeah. So that's why explaining everything's important. It's important. Now, when you're doing these, remember you're only doing a half car sim. So, like for a reference area, you only need to do half the frontal area, and it'll be accurate. Downforce drag, on the other hand, the true number will be twice this, because this is only recording what's on half the car. Monitors, don't worry about this. This will get set up automatically when we make a report. If you try to make a plot, it'll make a monitor as well. And again, the plot will be, yeah, it just tracks it over time. Make sure that you have everything set and all that when you do that. You can see residuals here. This probably doesn't make any sense to you if you haven't seen this before, but it's okay. Yeah, so those are plots. Now, onto scenes. So this is where those derived parts come into play, because when you make a scalar or a vector scene, you have to tell Star-CCM, I want these results on these parts here. So, for example, see how I have the pressure of the car on this plane? You have to make this on a derived part. Now, to make a derived part, what you do is you go to derived part and just say new part. So scalar scene, for example, this is called a section plane. as the name implies, it's a plane section of your domain. I'll take time to load now. And then also we have Streamlines too, which we use. Now, Streamlines take a little while to load. As you can see, Star-CCM is going, it's loading, all that. But again, you make this in derived parts as well. So let's just give that a second to load. Alright, so as you see, spaghetti everywhere. So you make streamlines in derived parts as well. So I'll show you just real quick the overview of that. I won't actually go into detail, but so go to section, plane. Oop, crap. Well, you need to choose where you make this as well, because it'll show up. So like, I usually just make it in geometry scene because it's cleaner. So you do like section, plane, you choose, so you see here that this is the plane it'll cut. You choose the normal, so obviously you want it normal to the X. So you specify that, and then you go and either select the exact origin you want or drag it, create, and yeah, that'll make it. Same thing with streamlines. So go to derived parts streamline. You can choose it to either be seeded at parts, which is what we did. It's kind of a mess. You can say line seed, so you draw like a line and then it'll generate streamlines along that line, or point, which would be the same thing but a point. Now, back to the scalar scenes and all that. So when you're making these scenes, what you do is you go scenes, new scene, you can make a new one, geometry or mesh, or scalar vector. So scalar scenes, you can add different displayers. So you can add, say, a new scalar scene, and in this case you can choose what you want the scalar field to be. In this case I chose it to be pressure, and then you can show it on any of the parts that you have made, either both derived or the surface ones you did. So just to show you what I mean, if you select all of them, give it a second. So those are all the section planes we made, and then I also had the pressure on the body as well. So that's why it helps to suppress some of these, just because it's a lot to look at. So like you can go through and look at certain cross sections at a time like that, and then if you want you can throw on the geometry just so you can see where you are on the car like that. Vector, it's basically the same thing, except this time you're dealing with vector fields instead. So on the vector, in this case I have velocity. I have that shut off right now, but let's turn off streamlines for a second. And so plane sections, if I go ahead and toggle the visibility there, now you can see that we have the velocity field on that plane section, and you can analyze from there. And then again, you can use like the streamlines and go ahead and look at that. But yeah, that's about it. So like I said, I'll make some more detailed videos in the future, but this was kind of an overview of the whole process.